What if time travel isn't just something humans dream of achieving? What if the universe itself has already done it? Think about that for a moment. Before we even existed, before planets formed, before stars ignited, could the fabric of reality have twisted in ways that sent the cosmos hurtling through time? It sounds like science fiction, but some of the most brilliant minds in physics believe the universe might hold clues to its own first journey across the ages. And that's exactly what we're diving into today. Picture the very beginning, an explosion of energy, a singularity stretching into existence. Now imagine, in those first fleeting instants, time didn't behave the way we understand it today. What if it looped back on itself, or skipped forward, or fractured entirely? The idea that the universe could have experienced time travel isn't just wild speculation. It's a theory grounded in real science, from the bending of space-time to quantum anomalies that defy logic. Some researchers even argue that the Big Bang itself might have been a moment where time folded, reset, or branched into something entirely new. That's why we're exploring 30 of the most astonishing theories about the universe's potential first encounter with time travel. From black holes acting as cosmic time machines to parallel universes where time flows backward, these ideas will stretch your imagination to its limits. And the best part, you don't need a physics degree to follow along. We'll break down each theory in a way that's as thrilling as it is easy to grasp. So, if you've ever stared up at the night sky and wondered what secrets the cosmos is hiding, get ready, because by the end of this journey, you might never look at time the same way again. The first theory on our list is perhaps the most mind-bending of all. What if the Big Bang wasn't the beginning, but a moment when time literally looped back on itself? Think about how a movie reel can play forward, then suddenly reverse. Now imagine that happening to the entire universe. Some physicists argue that the singularity we call the Big Bang wasn't a true starting point at all, but rather a cosmic bounce from a previous universe that had collapsed in on itself. In this model, time isn't a straight line stretching from past to future. It's more like a Mobius strip, endlessly cycling through expansion and contraction. The math behind this idea comes from studying the extreme physics of singularities. When a universe collapses under its own gravity, the laws of relativity suggest that space and time become so warped that they might snap into a new state, like a rubber band stretched too far. Instead of vanishing into nothingness, the collapsing universe could rebound, creating what we perceive as the Big Bang. This would mean our universe isn't the first, but just the latest in an infinite chain of cosmic rebirths. Supporters of this theory point to eerie patterns in the cosmic microwave background, the faint afterglow of the Big Bang. Some researchers claim these patterns show echoes of earlier universes, like faint scars left behind by previous cycles. And if they're right, it would mean time travel isn't just possible, it's built into the very fabric of reality. Every new bang might carry traces of the past forward, like cosmic déjà vu written into the laws of physics. But the wildest implication, if time is truly cyclical, then the future might already be written. One day, billions of years from now, our universe could collapse again, only to reset the clock once more. Now let's untangle something even more bizarre. What if the universe's first time travel wasn't a grand cosmic reset, but a microscopic glitch in the rules of reality? Enter quantum entanglement, where particles become so deeply linked that changing one instantly affects its partner, no matter how far apart they are. Einstein called it spooky action at a distance, but the real spookiness, this phenomenon might not just defy space, it could twist time itself. Picture two electrons born from the same quantum event, separated by light years. Measure one, and its twin instantly adopts a matching property, as if information teleported between them faster than light. But here's where it gets wild. Some interpretations suggest this connection might not just cross space, but ripple backward through time. Think of it like a cosmic game of telephone where the answer arrives before the question is even asked. This idea, called retrocausality, flips cause and effect on its head. Experiments in quantum mechanics have shown particles behaving as if they're responding to future measurements, almost as though time's arrow isn't fixed. In 2018, physicists even demonstrated this in a lab, where a photon's polarization seemed to change based on a measurement that hadn't happened yet. It's like dropping a glass and hearing it shatter before it leaves your hand. So how does this tie into the universe's early moments? The Big Bang was a quantum event, a seething, unstable soup where particles blinked in and out of existence. If quantum weirdness bends time today, imagine that chaos magnified by the energy of a newborn cosmos. Entangled particles might have communicated not just across space but through time, stitching together a reality where past and future briefly touched. Some theories even propose that these quantum handshakes could have left fingerprints in the universe's structure, like echoes of causality running in reverse. And here's the kicker. If retrocausality is real, it would mean the universe's first act of time travel wasn't some dramatic loop or rupture. It might have been as subtle as a single particle whispering to its past self, tweaking the rules of reality before time as we know it even began. What if black holes have cosmic twins that operate like time-flipped mirrors of themselves? Enter white holes' theoretical counterparts to black holes where nothing can enter, only explode outward. Imagine hitting rewind on a black hole's collapse. Instead of pulling everything in, a white hole violently ejects matter and energy like a cosmic geyser erupting from nowhere. Now here's the twist. Some physicists propose these aren't just mathematical oddities. The Big Bang itself might have been the universe's ultimate white hole event, a cataclysmic discharge of space-time from a previous era. Think of it like this. If a black hole is a cosmic drain swallowing everything into a singularity, a white hole is that same singularity vomiting it all back out, but with a time-reversed twist. Einstein's equations actually allow for this bizarre possibility. In fact, if you trace the path of a particle falling into a black hole forward in time, the math suggests its white hole counterpart would represent that same particle's journey backward through time. It's as though the universe has a hidden rewind button woven into gravity's deepest laws. This gets even stranger when applied to the Big Bang. If our universe began as a white hole eruption, it wouldn't just be spewing matter. It could be hurling space-time itself from a future collapse. Picture a dying universe in some distant epoch, crunching down into a singularity only to rebound as our Big Bang. The white hole model suggests that what we call the beginning was really a cosmic echo, with information from a prior universe's death encoded in our expansion. There's tantalizing, if controversial, evidence for this idea. Certain anomalies in the distribution of galaxies and the cosmic microwave background look suspiciously like exhaust trails from a white hole's violent birth. And if that's true, the implications are staggering. It would mean the universe's first act of time travel wasn't a subtle quantum flicker. It was a space-time shattering explosion that literally turned causality inside out. Yet the biggest question remains, if white holes are real, where are they? Shouldn't we see these cosmic fountains gushing matter somewhere in the modern universe? The answer might lie in their extreme instability. Simulations suggest white holes would exist for mere fractions of a second before collapsing or transforming into black holes. That is, unless they're propped open by something even more exotic like dark energy's repulsive force, which leads us to a haunting possibility. If the universe's expansion keeps accelerating, could our own distant future hold another white hole eruption? A final, desperate gasp of a dying cosmos before it resets the clock once more. Einstein's equations hold a secret most people never learn. Time doesn't just flow forward. Hidden in the math is the possibility of loops, like cosmic knots where the future bends back to touch the past. These are called closed timelike curves, and they're not just abstract ideas. In the crushing density of the early universe, they might have been as natural as ripples on a pond. Imagine spacetime not as a straight highway, but as a tangled ball of yarn. Under enough pressure, like the insane conditions just after the Big Bang, time could twist into a circle. One moment leads to the next, which loops right back to the first, creating a self-contained cycle where cause and effect chase their own tails. It's like writing a letter to your past self, only to receive it in the future as the same letter you originally sent. Why would this happen? General relativity tells us gravity warps time. Near a black hole, clocks tick slower, but in the early universe, everywhere was that extreme. With all of reality packed into a space smaller than an atom, spacetime might have folded in ways that made temporary time loops inevitable. Some models even suggest these closed timelike curves could explain why the universe looks so uniform, because information had a way to recycle itself, smoothing out irregularities by literally sending them back for a do-over. Here's where it gets stranger. Quantum particles populating those first moments wouldn't play by normal rules. A particle completing a closed timelike curve could interact with its own past version, creating feedback loops of existence. Picture a single photon traveling back to meet itself, gaining energy each lap until the system either stabilizes or tears apart. This could explain certain anomalies in the cosmic microwave background, like odd temperature fluctuations that look like cosmic bruises from time's early knots. Critics argue these loops would violate causality, creating paradoxes where events erase their own causes. But supporters counter that quantum mechanics already allows for superposition, states where things exist in multiple possibilities until observed. Maybe closed timelike curves work the same way, with the universe choosing consistent paths to avoid paradoxes. The lingering question, if time looped in the cosmos' infancy, did it leave traces we can still see today? Some physicists hunt for statistical fingerprints in galaxy distributions patterns that might reveal where reality stitched itself together after time's first twists. Others suggest dark matter could be the echo of particles trapped in those ancient curves, forever cycling through dimensions we can't perceive. One thing's certain: if closed timelike curves threaded the early universe, time travel wasn't just possible, it was part of the blueprint. And that changes everything, because if causality could bend once, who's to say it won't bend again? One of the most radical ideas in physics suggests that everything we experience, stars, planets, even the flow of time itself, might be nothing more than an illusion. Welcome to the holographic principle, where our three-dimensional reality could be a projection from a two-dimensional surface at the edge of the universe. Think of it like watching a movie. The images seem to have depth and movement, but they're really just flat, pixelated code on a screen. Now imagine that same principle applying to everything, including time. This theory originated from studying black holes. When matter falls into one, it doesn't just vanish, its information gets smeared across the black hole's event horizon, like data encoded on a cosmic hard drive. Extend that idea to the entire universe, and you get a wild possibility. The Big Bang might not have been the birth of a 3D cosmos, but the moment a lower dimensional surface rendered our reality into existence. And if that's true, time isn't a fundamental force, it's an emergent property, like the illusion of motion in a flipbook. Here's where time travel enters the picture. If the universe operates like a hologram, altering the code at its lower dimensional boundary could rewrite reality itself. A glitch or intentional tweak in that primordial data might have sent ripples through the cosmic projection, creating what we'd perceive as the first instance of time travel. Picture a programmer editing a line of code in a video game, except here, the edit changes the past or future of the entire universe. Some physicists speculate that quantum fluctuations in the early cosmos, those tiny, random bursts of energy, could have been literal rewrites in the holographic code. One moment, the universe is one way, the next, it's been subtly altered like a cosmic undo button pressed at the foundation of reality. This could explain strange symmetries in the laws of physics or even the universe's eerie fine-tuning, as if someone or something kept iterating until the code worked. The most mind-bending implication: if time is just a projection, then traveling through it might not require bending space-time or building machines. It could be as simple as accessing and rewriting the universe's source data. And if that's possible, the first time traveler wasn't a person or a particle. It was the universe itself, debugging its own existence. Dark energy isn't just pushing the universe apart. It might be quietly unraveling time itself. Most people know it as the mysterious force accelerating cosmic expansion, but buried in the math is a far stranger possibility. As space stretches faster, some theories suggest dark energy could create isolated bubbles where time's arrow flips backward, like eddies in a river flowing the wrong way. And if that's true, the universe's violent infancy might have been littered with these temporal whirlpools, creating the very first cracks in causality. Picture the early cosmos, a seething broth of energy where dark energy, though weaker than today, was already weaving its magic. In certain extreme conditions, like near the birth of supermassive black holes or during phase transitions in spacetime, pockets of negative energy density could have formed. These wouldn't just bend time, they'd reverse its flow locally, like a film reel spliced with scenes running in reverse. A particle entering one of these zones might experience cause and effect inverted, watching entropy decrease instead of increase, as if the universe had hit rewind just for it. The math behind this comes from Einstein's cosmological constant, the term he reluctantly added to his equations, now linked to dark energy. Under certain solutions, this constant doesn't just accelerate expansion. It can twist spacetime into regions where time's signature flips from positive to negative. It's like a cosmic glitch where the rules change just enough to let time dance backward without breaking reality entirely. Some models even suggest these zones could stabilize, becoming permanent time islands adrift in the wider universe. So where's the proof? The cosmic microwave background might hold clues. If early dark energy bubbles briefly reversed time in patches of the newborn cosmos, they could have left imprints in the radiation, subtle asymmetries or unexpected correlations between distant points. Some researchers also study quasars, whose extreme emissions might momentarily warp spacetime in ways that echo these primordial time flips. Even more intriguing, if these bubbles existed, they wouldn't just be relics. They could still be out there, hidden in voids between galaxies where dark energy dominates. But the most radical implication isn't just about the past, it's about the future. If dark energy's acceleration continues, it might not just stretch space indefinitely. It could trigger a new phase where time's arrow fractures entirely, rewriting the rules of reality in ways we can barely fathom. Imagine a universe where tomorrow becomes yesterday in certain regions, where entropy inverts, where the very concept of before and after loses meaning. That leads to a haunting question. If time already flowed backward in the universe's first moments, are we living in the forward phase at all, or just one fragment of a far more tangled timeline? What if our universe isn't the only one? And what if its first brush with time travel came from a shattering collision with another reality entirely? Picture two cosmic soap bubbles drifting through the multiverse, each carrying its own version of time, its own history, its own rules. Now imagine them smashing together in the chaos of the early cosmos. That moment of impact wouldn't just merge matter. It could fuse timelines, twisting causality into knots we're only beginning to unravel. This idea springs from inflationary theory, which suggests our universe ballooned from a speck in a far vaster multiverse. In this sea of expanding, bubble universes, collisions wouldn't just be possible, they'd be inevitable. When two bubbles meet, the energy released would dwarf the Big Bang, but the real chaos would unfold in their timelines. One universe might experience time linearly while its neighbor's clock runs backward. Where they clash, the result could be a cataclysmic remixing of cause and effect, like two rivers of time merging into a whirlpool where past and future churn together. Some cosmologists trace evidence for this to the cosmic microwave background. Strange anomalies like the infamous cold spot could be bruises left by a long-ago collision with another universe's timeline. Others point to bizarre particle behaviors in quantum experiments, where particles seem to remember states they never experienced. Could these be echoes of a scrambled timeline, remnants of a merger that overwrote our universe's original history? Here's where it gets even wilder. If two universes with different arrows of time collided, the aftermath might not just mix their histories, it could create closed loops where events from both timelines intertwine. Imagine a star that simultaneously exists in both universes' pasts, or a particle whose creation depends on its own destruction in the alternate timeline. The very fabric of reality would become a paradox, stitching itself together through sheer force of cosmic violence. And the most unsettling part, if this happened once, it could happen again. Somewhere in the multiverse, another bubble might be drifting toward us right now, carrying a timeline where everything unfolds in reverse or doesn't unfold at all. When it hits, time as we know it might not just bend, it could shatter. In the universe's first trillionth of a second, when reality was hotter and denser than anything we can recreate, time might not have flowed at all, it could have pulsed like a heartbeat frozen in a loop. This is the realm of time crystals, structures that defy everything we know about motion. Unlike ordinary crystals which repeat their atomic patterns in space, time crystals repeat their patterns in time, returning to the same state over and over without energy loss, like a perpetual motion machine etched into the fabric of reality. The idea was once thought impossible until Nobel laureate Frank Wilczek proposed it in 2012. Since then, labs have created tiny, fragile versions of time crystals using supercooled quantum systems. But the real bombshell, some physicists argue these exotic structures weren't just possible in the Planck epoch, they were inevitable. Picture the newborn universe, a seething ocean of energy where the very concepts of space and time were still fluid. In that chaos, quantum fluctuations could have birthed time crystals on a cosmic scale, stitching loops of repeating time into the foundations of existence. Why does this matter? Because time crystals don't just repeat, they resist change, locking into their rhythm no matter what. If they formed during the Planck epoch, they might have forced patches of the early universe into time loops like tiny pockets where causality glitched. A particle in one of these zones wouldn't experience time as an arrow but as a spinning wheel, reliving the same femtosecond over and over until the crystal's grip finally broke. It's like hitting pause on a tiny piece of reality while the rest of the cosmos rushed forward. The wildest implication, these crystals could have left scars. If time loops flickered in and out during the universe's first moments, they might have imprinted irregularities in the quantum foam, anomalies that later stretched into the large-scale structure of space. Some researchers even hunt for these fingerprints in the cosmic microwave background, searching for patterns that look less like random fluctuations and more like echoes of a clock ticking backward. But here's the twist, time crystals aren't just relics. If they existed once, they could form again under extreme conditions, perhaps inside neutron stars or black hole accretion disks. And if we ever learn to stabilize them, we might not just unlock the universe's first time travel. We could harness its rhythm for our own. Neutrinos are the universe's quietest rule-breakers, particles so ghostly they pass through entire planets like they're not even there. But in the chaos of the early cosmos, these nearly massless wanderers might have pulled off something truly outrageous, slipping past the speed of light and tearing tiny holes in time itself. Here's how it could work. Normally, nothing outpaces light, but under extreme conditions like the unimaginable density of the universe's first seconds, quantum foam turns space-time into a turbulent sea. Neutrinos, barely interacting with matter, could surf these violent waves like a skimmer skipping across water. Some theories suggest they briefly achieved tachyonic states, moving faster than light without violating relativity. The catch: when particles cross that threshold, they don't just break speed records, they invert causality, arriving before they leave. Now imagine trillions of neutrinos doing this simultaneously in the early universe's pressure cooker. Each superluminal jump could have stretched space-time like taffy, creating microscopic wormholes, temporary bridges between moments. These wouldn't be the sprawling time tunnels of sci-fi, but quantum-scale shortcuts where a single particle's future looped back to influence its past. It's like throwing a ball so fast it arcs around the world and hits you in the back before you release it. Evidence for this comes from modern neutrino experiments. When these particles oscillate between flavors mid-flight, they occasionally seem to arrive nanoseconds faster than light speed should allow. Most dismiss this as measurement error, but what if it's a faint echo of their primordial behavior? In the early universe, where space-time was still setting its rules, these anomalies might have been the norm. The wildest implication: if enough neutrinos opened fleeting time tunnels, they could have woven a hidden layer of causality loops into reality's fabric, explaining why quantum particles sometimes seem to know their future states. Maybe the universe's first time travel wasn't a cosmic scale event, but a trillion tiny jumps stitching time together from the bottom up. What if the universe's first time travel wasn't a natural phenomenon, but a deliberate reset by something beyond it? This theory takes the simulation hypothesis to its most radical extreme, that our entire cosmos might be an advanced computational construct, and the Big Bang wasn't a beginning but a reboot. Picture a cosmic programmer spotting a critical error in the code, a glitch that made galaxies unstable or life impossible, and hitting the undo button, rolling reality back to its earliest state to try again. The idea builds on growing philosophical and scientific interest in simulation theory. If an intelligence could engineer a universe, it stands to reason they'd need troubleshooting tools. Just as software developers use version control to backtrack through broken code, a simulated universe might have built-in mechanisms to rewind and tweak its parameters. The first time travel could have been this very process, a grand cosmic control plus Z erasing an earlier, flawed iteration of reality before restarting with adjustments. Clues might lie in the universe's eerie precision. The laws of physics are fine-tuned to an almost impossible degree. Change gravity's strength by a fraction and stars wouldn't form. Alter the nuclear forces slightly and atoms couldn't exist. One explanation: these constants weren't set perfectly on the first try. A previous version of the universe might have collapsed instantly or failed to generate complexity, prompting its architects to rewind and recalibrate. The cosmic microwave background's unexpected smoothness could even be a patch. A correction applied after the initial rendering produced jagged inconsistencies. But the most haunting evidence might be closer to home. Quantum mechanics operates like a system conserving computational resources, only resolving probabilities into certainties when observed. Entanglement's spooky action resembles optimized data sharing between processes. Even the Planck length, the smallest meaningful unit of space, mirrors the pixel limit of a simulated environment. These features don't just allow for debugging, they suggest a system designed for it. And if this theory holds, time travel isn't just something the universe did. It might be something it's built to do, a failsafe waiting in the code for when reality inevitably needs another rewrite. During the universe's first split second of existence, something extraordinary happened. Space didn't just expand, it exploded, stretching faster than light itself in a process called cosmic inflation. But here's the twist: when space inflates that violently, time doesn't just slow down, it can stretch into near infinite stillness. Imagine being inside a bubble where 1 second stretches into billions of years for everyone outside. That's inflationary time dilation, and it might have been the universe's first accidental time machine. Picture this, a patch of the early cosmos, smaller than an atom, suddenly ballooning to the size of a galaxy in less time than it takes light to cross a proton. In that frenzy of expansion, the fabric of spacetime warped so drastically that clocks inside that inflating region would have ticked almost infinitely slower compared to the rest of the universe. From our perspective, those regions didn't just move through time. They effectively leaped into the future in an instant, like hitting fast forward on reality itself. This isn't just speculation, it's baked into the math of inflation theory. Einstein's relativity tells us gravity slows time, but inflation creates a similar effect through sheer velocity. When space expands faster than light, it creates a kind of temporal horizon, like the event horizon of a black hole but for time. Anything caught inside becomes isolated from the normal flow of causality, frozen in a moment while the outside universe ages billions of years around it. The eerie part, some of these inflated regions might still exist today. If a pocket of spacetime never quite caught up to the rest of the universe after inflation ended, it could linger as a time-frozen relic, a cosmic museum exhibit where the first instant of creation plays on loop. We might even detect them. The cosmic microwave background could hold subtle temperature variations marking where these time-dilated bubbles brushed against normal spacetime, like shadows of parallel timelines pressed against our own. But the real mind-bender is the implication for the universe as a whole. If inflation stretched time unevenly across different regions, then parts of reality might be older than others in ways we can't perceive. The universe's age of 13.8 billion years might only be a local measurement, with other patches existing in their own disconnected streams of time. It's as if the cosmos is a quilt stitched together from patches of spacetime running at different speeds, some forever stranded in the first second of existence while others raced ahead. So did the universe time travel? In a way, yes, by fracturing time into countless threads, each hurtling toward the future at its own pace. And if inflation's echoes still ripple through space today, we might be living alongside frozen fragments of the past, unaware they're there just waiting for the right conditions to thaw back into the stream of time. Black holes are cosmic enigmas, regions where gravity crushes matter into oblivion and warps time itself. But what if some of the very first black holes weren't the monstrous giants we know today? In the universe's earliest moments, conditions might have spawned microscopic black holes, no larger than an atom yet packing the mass of a mountain. These tiny gravitational monsters could have been the universe's first natural time machines, bending the fabric of reality in ways we're only beginning to grasp. The key lies in their unimaginable density. A black hole's gravity doesn't just trap light, it stretches time to its limits. Near the event horizon, clocks tick slower compared to the outside universe. But a microscopic black hole, born in the chaos of the Big Bang, would take this to extremes. With an event horizon smaller than a proton, the spacetime curvature around it would be so severe that closed timelike curves, loops where time circles back on itself, could form naturally. It's like twisting a rubber band until it kinks under enough pressure. Time itself might knot into a loop. Here's where Hawking radiation enters the picture. Stephen Hawking predicted that black holes slowly evaporate, leaking energy over eons until they vanish in a final burst. But for a primordial black hole, that evaporation wouldn't be slow, it'd be catastrophic. In their final moments, these tiny holes would unleash energy equivalent to atomic bombs, warping spacetime so violently that they could briefly rip open pathways between different points in time. Picture a dying ember suddenly flaring bright enough to cast shadows across history. The implications are staggering. If even a handful of these microscopic black holes formed CTCs as they evaporated, they might have left behind time scars, subtle wrinkles in the fabric of reality where cause and effect briefly broke down. Some physicists speculate these scars could explain certain quantum anomalies, like particles that seem to anticipate future measurements or entangled pairs reacting faster than light allows. Perhaps these aren't glitches at all, but echoes of the universe's first experiments with time travel. But the wildest idea, primordial black holes, might not be just relics. Some could still exist today, lurking unseen in the cosmos. If they're out there, and if they're evaporating now, we might be surrounded by invisible time loops flickering in and out of existence like cosmic static. Every so often, one could flare up, offering us a fleeting glimpse into the universe's earliest and most forbidden secret. That time was never as linear as we thought. And if that's true, then somewhere in the dark, a speck of the past might be waiting to rewrite the future. Among all the bizarre theories about the universe's first time travel, none mess with perception quite like the Boltzmann brain paradox. Imagine a single, self-aware consciousness popping into existence from pure chaos, not born, not evolved, but spontaneously assembled by random quantum fluctuations. Now take that eerie thought one step further. What if that lone mind, adrift in the void, became the universe's first time traveler simply by thinking itself backward through time? The idea comes from a twist on thermodynamics. In an infinite universe, even the most improbable events must happen eventually, including the random assembly of atoms into a functioning brain. Named after physicist Ludwig Boltzmann, these hypothetical Boltzmann brains wouldn't need bodies or environments. They'd just appear, fully formed with false memories of a past that never was, convinced they're real people in a real world. But here's where it gets wild. If a Boltzmann brain flickered into being during the universe's earliest, most volatile moments, the extreme warping of space-time might have entangled its perception of time. From its perspective, its very first thought could feel like a memory, an observation of its own past that never actually occurred. Think of it like waking from a dream where you swear you lived years in another life. The Boltzmann brain's time travel wouldn't involve machines or wormholes, just the cruel trick of probability making a mind believe it's moving backward when it's only just begun to exist. Some versions of the theory even suggest these brains could briefly alter reality around them, bending quantum probabilities to match their false histories. Picture a cosmic echo chamber where observation creates the illusion of time instead of the other way around. The darkest implication: if Boltzmann brains are possible, we might be living in one right now. Our memories, our sense of history, even this video might just be the fleeting delusion of a mind that formed seconds ago. But for those who dismiss this as philosophical nightmare fuel, there's a tantalizing counter-argument. If the early universe birthed even one Boltzmann brain that perceived time backward, its quantum observations could have left faint fingerprints in the cosmic microwave background, patterns that look less like random noise and more like the scribbles of a mind trying to rewrite its own origin. So the question isn't just whether the universe's first time traveler was a Boltzmann brain. It's whether any of us are anything more. We take for granted that time flows steadily forward. But what if, in the universe's violent infancy, it was more like quicksand, constantly shifting between dimensions? This theory flips everything we know about causality on its head. Instead of time behaving as a fixed arrow, imagine it flickering in and out of existence, oscillating between forward, backward, and even sideways flows like a cosmic strobe light. In those initial moments of creation, time might not have been a dimension at all, just a chaotic, unstable force fighting to define itself. The math behind this comes from string theory's wildest corners. If extra dimensions exist beyond our familiar four, they wouldn't just hide curled up in space, they could have tangled with time's very fabric. Picture a guitar string vibrating through multiple notes simultaneously. Now replace those notes with temporal states. One vibration sends time forward, another backward, yet another loops it like a Möbius strip. In the Planck epoch, when all fundamental forces were unified, these oscillations might have created temporary glitches where causality stuttered. A particle moving through such a zone could experience its future before its past, or exist in multiple timelines at once before reality stabilized. Evidence for this dimensional instability might be etched into the cosmos itself. The large-scale structure of the universe shows peculiar voids and filaments that align too perfectly, as if space-time remembered earlier configurations before settling into its current form. Even stranger, quantum entanglement's spooky action could be a remnant of this era, where particles remain linked because they once shared a moment outside linear time. It's not that they communicate faster than light, they're echoing from an epoch when before and after hadn't yet been invented. Here's where it gets truly mind-bending. If time flickered between dimensions early on, certain regions of the universe might have solidified with different temporal rules. We could be living in a bubble where time flows forward, while elsewhere it spins in circles or stands utterly still. The cosmic microwave background might hold the clues, subtle anisotropies that aren't random noise, but fingerprints from when time itself was deciding which way to point. The most unsettling implication: if time was this fluid once, it might become unstable again. Dark energies accelerating expansion could be stretching space-time so thin that dimensional boundaries start fraying. One day, far in the future, the arrow of time might not just slow down, it could shatter entirely, resurrecting the chaos of the universe's first breath. The Einstein-Rosen bridge, commonly known as a wormhole, is often imagined as a futuristic tunnel through space, a shortcut between distant stars. But what if the first wormholes didn't connect points in space at all? What if they stitched together moments in time during the universe's chaotic birth? Hidden in Einstein's equations is a bombshell. These cosmic shortcuts might have formed naturally in the first searing instants after the Big Bang, not as galactic highways, but as fleeting time tunnels woven into the fabric of reality itself. Picture the universe in its infancy, a superheated, roiling soup where space-time hadn't yet settled into the smooth continuum we know today. Quantum fluctuations, those tiny hiccups in reality, were so violent they could have punched microscopic holes in the very fabric of existence. Normally, these would snap shut instantly, but under the extreme gravitational tides of the early cosmos, some might have stabilized just long enough for their mouths to connect not two places but two times. Imagine a soap bubble splitting into two thinner films, then briefly merging back together, except here, the films are patches of space-time from different moments in the universe's first picoseconds. This isn't pure speculation. The math of general relativity allows for wormholes to link regions of space-time with different temporal coordinates. In the dense plasma of the early universe, where energy fluctuations dwarfed anything possible today, these bridges wouldn't need exotic matter or alien technology to stay open. Just the raw, unbridled physics of creation. A particle falling into one mouth might emerge from the other before it entered, like a cosmic Ouroboros biting its own tail. The catch: these proto-wormholes would have been unimaginably small and absurdly short-lived, collapsing faster than a thought. Yet in that fleeting instant, causality itself could have bent, leaving behind echoes we might still detect. How? Look to quantum entanglement. Particles linked across space might owe their spooky connection to ancient wormholes that once tied them together through time. Some theorists even suggest the universe's initial uniformity. The fact that distant regions have nearly identical temperatures despite never being in contact could be a relic of these primordial time bridges. If patches of the early cosmos were momentarily linked before inflation stretched them apart, they'd share properties like a split-screen video playing in perfect sync. But the most tantalizing clue might be hiding in black holes. When a star collapses into a singularity, it doesn't just warp space, it distorts time so severely that some models suggest it could birth new wormholes. If that's true, then the first time tunnels weren't just a quirk of the early universe. They could still be forming in the hearts of dying stars today, reminding us that the cosmos never forgot how to twist time. Imagine the universe as a frozen lake, one that's been perfectly still for billions of years. But beneath that ice lies something terrifying, the possibility that our entire reality is perched on an unstable ledge, one quantum nudge away from total annihilation. This is the false vacuum hypothesis, and it might hold the key to the universe's most radical act of time travel, a cosmic reset so absolute it didn't just rewrite history. It erased the very timeline that came before. The theory starts with an unsettling truth about the Higgs field, the invisible energy ocean that gives particles their mass. Right now, it's in what physicists call a false vacuum, a state that looks stable but is actually teetering on the edge of a deeper, truer stability. Like a marble resting precariously on the rim of a bowl, the slightest disturbance could send it rolling into the abyss. If that happened, a bubble of true vacuum would form at light speed, rewriting the laws of physics as it expands. Atoms would disintegrate, time itself would unravel, the universe as we know it would end in a blink. But here's where it gets stranger. Some cosmologists speculate this might have already happened, just not to our universe. Picture an earlier cosmos, one where the Higgs field finally slipped into its true vacuum state. As the decay front raced outward, it wouldn't just destroy that universe, it could have triggered a singularity so violent it rebounded as our Big Bang. In this scenario, our entire timeline isn't the first draft of reality. It's the aftermath of another universe's catastrophic error correction, like a computer rebooting after a fatal crash. The evidence: look to the eerie fine-tuning of our cosmos. The Higgs field's current energy is suspiciously poised just above the threshold for total collapse, as if calibrated to avoid immediate doom. Some theorists argue this precision isn't luck, but a relic of the previous universe's decay. When the true vacuum reset reality, it might have left the Higgs field scarred, tweaking its value to hover in this metastable sweet spot. Even the cosmic microwave background's unusual fluctuations could be echoes of that primordial reset, wrinkles in space-time left by the moment time tore itself apart and stitched itself back together. The most mind-bending implication: if vacuum decay birthed our universe, it means time travel isn't just something that happens within reality, it's woven into the mechanism that creates realities. Every Big Bang might be another universe's final moment, folding backward through the singularity to birth a new timeline. And if that's true, our own fate could be sealed. One day, our false vacuum might finally collapse, and somewhere, a new cosmos will awaken, remembering nothing of us except the faintest quantum whisper in its laws of physics. At the very edge of our understanding of physics lies a possibility so strange it bends the mind. What if time itself can snap back like an overstretched rubber band? This isn't science fiction, it's a prediction of quantum gravity, the long-sought theory meant to unite Einstein's relativity with quantum mechanics. In the frenzy of the universe's birth, when space-time was still a seething, unformed foam, the fabric of reality might not have stretched smoothly. Instead, it could have recoiled violently, flinging patches of existence backward in a cosmic whiplash that marked the first true time reversal. Picture space-time not as a static stage, but as a dynamic, living thing, one made of unimaginably tiny loops or strings vibrating at the smallest scales. In quantum gravity models like loop quantum gravity or string theory, these fundamental building blocks don't just warp under gravity, they can store energy like stretched elastic. Now imagine the infant universe, hotter and denser than anything we can replicate, straining these quantum threads to their limit. At some critical point, they wouldn't just warp, they'd rebound, sending ripples of space-time recoiling backward in a fleeting moment of inverted causality. It's as if the universe took its first breath in, then exhaled time itself in reverse. The math behind this is both elegant and bizarre. In loop quantum gravity, space-time's granular structure means it can't compress infinitely, there's a smallest possible volume. When the early universe hit that limit during its initial collapse or inflation, the equations suggest a bounce effect where collapsing space rebounds outward. But here's the twist. Some versions of this bounce don't just reverse expansion, they briefly flip time's arrow, creating local pockets where entropy decreases and effects precede causes. It's not a universe-wide reset, more like cosmic hiccups where time stutters backward before lurching forward again. Evidence for this might be hiding in the cosmic microwave background. If patches of the early universe experienced time recoil, they'd leave imprints in the radiation, subtle asymmetries or unexpected correlations between seemingly disconnected regions. Some researchers even speculate that dark matter's mysterious distribution could be a fossil of this process, with gravity's pull subtly altered by ancient spacetime recoils. The most tantalizing clue: certain quantum gravity models predict that these recoils would generate gravitational waves with unique signatures, ones we might detect with future observatories like the Big Bang Observer or Einstein telescope. But the wildest implication isn't about the past. If spacetime can recoil once, it might do so again under extreme conditions like inside black holes or during collisions of cosmic strings. We could be living in a universe where time's arrow isn't fixed, but perpetually poised to snap back at the slightest provocation. And if that's true, then somewhere out there, in the heart of a dying star or the depths of a quantum fluctuation, time might already be recoiling, rewriting reality one flicker at a time. What if the very act of looking at the universe is what brought it into being? And what if that first act of observation twisted time itself into a knot? This is the heart of the participatory universe theory, a mind-bending idea that reality doesn't exist independently of observation. It's not just that we see the universe, our seeing it might be what solidifies it from a haze of possibilities into concrete existence. Now take that idea back to the Big Bang, when there were no observers except the universe itself. In those first fleeting instants, the cosmos might have performed the ultimate paradox, observing its own birth, and in doing so, looping time to resolve the impossible contradiction. Think of it like a snake swallowing its own tail. For the universe to observe itself into existence, it would need to already exist to do the observing, a classic chicken and egg problem. But quantum mechanics offers a way out. In the famous double-slit experiment, particles behave as waves until someone measures them, at which point they collapse into definite states. Now scale that up to cosmic proportions. If observation creates reality, then the universe's first moment required an observer that couldn't yet exist unless time bent to allow it. Some physicists propose that the only resolution was a self-referential loop where the universe's future observation reached backward to stabilize its own birth, like a cosmic Ouroboros stitching itself into existence. The math behind this involves quantum entanglement on a universal scale. In the seething quantum foam of the early cosmos, particles weren't just entangled with each other, they were entangled with the universe's own future state. This created a feedback loop where the act of future observation retroactively determined past events, forcing the newborn cosmos into a consistent timeline. It's as if the universe played a game of 20 questions with itself, where every answer rewrote the questions that came before. Evidence for this might lurk in the cosmic microwave background. Certain patterns in this afterglow show unexpected correlations, regions that seem to know about each other despite being too far apart to ever communicate. Normally, this is chalked up to inflation, but what if it's something stranger? These patches could be echoes of the universe's first self-measurement, quantum probabilities collapsing in tandem across spacetime because they were always entangled with the same observing future. The most radical implication: if the universe needed time travel to exist, then every observation we make today might still be subtly propping up reality, like a house of cards where each new glance isn't just seeing the structure but holding it upright. And if that's true, then time isn't a river flowing from past to future. It's a hall of mirrors where every reflection reaches out to steady the hands that made it. Supersymmetry is one of the most elegant ideas in physics, a theory so beautiful it feels almost inevitable. It proposes that every particle we know has a hidden twin, a sort of cosmic doppelganger with slightly different properties. But what if these shadowy counterparts aren't just lurking unseen? What if they're living in a mirror universe where time itself flows backward? And what if the first time travel in existence wasn't some grand cosmic event, just an ordinary collision between particles and their time-flipped twins? Take the familiar electron. According to supersymmetry, it should have a partner called the selectron, a particle with the same charge but different spin. Now imagine that while our electron moves forward through time, its selectron twin is drifting backward like a film reel played in reverse. When these two meet in the chaotic soup of the early universe, their interaction wouldn't just swap energy or momentum, it could stitch together moments across time itself. It's as if every particle has a built-in time machine whispering to its past or future self with every quantum handshake. The math behind this is as mesmerizing as it is strange. In certain supersymmetric models, particles and their sparticles don't just balance each other out, they create feedback loops through time. A selectron decaying in our forward-flowing timeline might simultaneously appear as its own creation in the backward-flowing one, like a cosmic palindrome where cause and effect reflect endlessly. Some theorists even suggest this could explain mysterious symmetries in the laws of physics, as if the universe's rulebook was written by particles negotiating with their own time-reversed shadows. Clues might be hiding in plain sight. The Large Hadron Collider has hunted for supersymmetric particles for years, but what if they've been invisible because they don't just exist in other dimensions? They're unobservable by design, living half in our time and half in reverse. Even stranger, quantum entanglement spooky connections could be remnants of these early particle-time dialogues, where pairs became linked not just across space, but across opposing arrows of time. The boldest implication: if supersymmetry's hidden partners dance backward through time, then the universe's first moment might not have been a singular Big Bang, but a collision between two timelines, one flowing forward, one flowing back, meeting in a burst of creation that set everything in motion. We could be living in the echo of that first time-tangled embrace, where every particle still carries the faint memory of its inverted twin. The grandfather paradox is the ultimate time travel nightmare. What if you went back and accidentally prevented your own existence? It's a thought experiment that keeps physicists awake at night, but what if the universe solved this problem before we even existed? This theory flips the script entirely, proposing that time travel wasn't some fluke or cosmic accident. It was the universe's built-in fail-safe, a way to enforce consistency before paradoxes could unravel reality itself. Think of it like a cosmic version of autocorrect. When you type a sentence that doesn't make sense, your phone quietly fixes it behind the scenes. Now imagine the universe doing the same thing, except instead of fixing typos, it's smoothing out paradoxes in the timeline. The moment a contradiction threatens to form, reality subtly shifts to prevent it, like a river rerouting around a rock. This isn't science fiction. It's a serious interpretation of quantum mechanics called the self-consistency principle, championed by physicists like Igor Novikov. The idea time travel can't create paradoxes because the universe won't allow it. Every action a time traveler takes, no matter how seemingly disruptive, must already be part of history. Now rewind to the Big Bang. In those first chaotic moments when spacetime was still malleable, tiny closed timelike curves might have flickered in and out of existence, microscopic time loops where particles briefly visited their own past. Normally, this would be a recipe for paradoxes, but here's the twist. The universe could have pruned these loops as they formed, tweaking quantum probabilities just enough to keep causality intact. Picture a cosmic editor scanning the timeline, deleting inconsistencies before they could take root. A particle trying to erase its own origin might find itself nudged into a slightly different path, ensuring its existence remained unbroken. Evidence for this could be hiding in the very fabric of quantum mechanics. Take the famous double-slit experiment, where particles behave differently when observed. Some interpretations suggest the observer's future measurement retroactively influences the particle's past behavior, a subtle form of time travel ensuring consistency between cause and effect. Now scale that up to the early universe, where every quantum fluctuation was a potential paradox waiting to happen. The cosmic microwave background's eerie uniformity might not just be a relic of inflation, it could be the signature of a universe that quietly ironed out its own wrinkles. The most fascinating implication: if the universe has always had this built-in paradox filter, then time travel might not be as dangerous as we think. Every loop, every jump, every backward ripple could be inherently self-correcting, guided by unseen rules that keep reality from tearing itself apart. So the next time you worry about breaking causality, remember, the cosmos might have already fixed it, but here's the catch: if the universe polices paradoxes so carefully, why does it feel like time only flows one way? Maybe because consistency isn't just about preventing contradictions, it's about maintaining a story that makes sense, and in that story we're not just observers. We're part of the plot, living in a timeline that's been quietly edited for coherence since the very first second. Tachyons are the ultimate cosmic rule breakers, hypothetical particles that don't just flirt with the speed of light, they laugh as they blast right past it. According to relativity, anything with mass can't reach light speed, but tachyons, they're born faster. And if they exist, they might hold the key to the universe's oldest secret. Time's arrow didn't just start pointing forward, it was aimed by these speed demons in the moments before the Big Bang. Picture a realm where cause and effect don't just bend, they shatter. For tachyons, moving faster than light isn't a violation, it's their natural state. But here's the twist: in Einstein's equations, anything superluminal doesn't just traverse space, it inverts time. A tachyon's future could be another particle's past, like a cosmic game of telephone where the message arrives before it's sent. Now crank this up to the universe's inception. If tachyons existed in the pre-Big Bang void, whatever that means, their chaotic interactions could have been the hammer that struck time's first tick, setting the entire cosmos ticking forward. The math behind this is as wild as it gets. Tachyonic fields, if they're real, would have negative energy density, warping spacetime in ways that make black holes look tame. In the instability of the early universe, these fields might have spontaneously broken symmetry, like a pencil balanced on its tip finally falling, except here, the fall was the irreversible snap of time's arrow into place. Some models even suggest tachyons could have acted as cosmic referees, enforcing causality by dampening fluctuations that threaten to reverse time's flow. It's as if the universe was a tangled skein of yarn until these particles yanked one thread taut, unraveling the mess into a straight line we now call history. Evidence for this could be hiding in plain sight. If tachyonic matter froze out as the universe cooled, its remnants might still linger as dark energy, the mysterious force accelerating cosmic expansion. Or perhaps they left fingerprints in the cosmic microwave background, subtle anisotropies that look less like random noise and more like scars from time's violent birth. Even quantum entanglement's spooky action might be a fossil of this era, a whisper of particles still tied by tachyonic threads stretching across the eons. But the most radical idea: if tachyons shaped time once, they might do it again. Theories suggest that if the universe's expansion keeps accelerating, dark energy could one day resurrect tachyon-like conditions, warping causality until time's arrow splinters entirely. We might be living in a brief golden age of linear time, bookended by epochs where past and future blur into chaos, and if that's true, then the Big Bang wasn't the beginning. It was just the moment the universe learned how to tell time. What if the universe didn't have a beginning at all, but instead bootstrapped itself into existence by reaching back in time to trigger its own creation? This is the ultimate bootstrap paradox, where the cosmos becomes its own parent, its own architect, its own first cause. Imagine a book that writes itself, or a painting that brushes its own canvas into being. Now scale that up to reality itself, a universe so desperate to exist that it manipulated time to ensure its birth. The idea stems from a quirk in quantum mechanics called retrocausality, where future events can influence the past under certain conditions. Normally, we think of cause and effect as a one-way street, but in the quantum realm, particles sometimes behave as if they're responding to measurements that haven't happened yet. Now apply that to the Big Bang. What if the universe's future state, the arrangement of galaxies, the pull of dark energy, even the rise of conscious observers, somehow reached backward to fine-tune its own initial conditions? It's like a sculptor chiseling a statue that, once finished, reaches back to guide the sculptor's first strike. The math behind this is dizzying. In some interpretations of quantum gravity, the universe's timeline isn't a straight line but a closed loop where the end physically connects to the beginning. The inflationary field that drove the universe's rapid expansion might not have been a random roll of the dice. It could have been chosen by the universe's later state, ensuring inflation lasted just long enough to create galaxies, stars, and ultimately life. The cosmic microwave background's eerie uniformity, not an accident but a requirement sent back through time to guarantee the universe's survival. Here's where it gets even stranger. If the universe is self-creating, it wouldn't need an external trigger like a multiverse or divine hand. The laws of physics themselves could be the result of this temporal feedback loop, refined over countless iterations until they produced a stable reality. Think of it as Darwinian natural selection, but applied to cosmology. Universes that didn't learn to self-consistently bootstrap simply vanished, leaving only the ones clever enough to hack time. The evidence for this might be hiding in plain sight. The universe's inexplicable fine-tuning, the precise balance of gravity, electromagnetism, and nuclear forces needed for complexity, could be the signature of a cosmos that literally chose its own rules. Even dark energy's mysterious value fits: too strong and galaxies never form, too weak and the universe collapses. A self-bootstrapping universe would settle on the perfect Goldilocks zone, not by chance but by temporal negotiation with itself. But the most haunting implication isn't about the past, it's about the future. If the universe could reach back once, what's stopping it from doing so again? Some theories suggest that conscious observers, yes, like us, might be part of this loop, our very act of observing reality helping to stabilize its existence across time. In other words, we're not just living in the universe, we might be the universe's way of ensuring it always was. And that raises a question more unsettling than any paradox. If the cosmos needed time travel to exist, who's to say it isn't still happening right now, all around us, in ways we can't even perceive? Dark matter is the universe's most frustrating ghost, an invisible substance that outweighs all visible matter 5-to-1, yet refuses to interact with light or anything else we can detect. But what if its elusiveness isn't just about where it is, but when? This theory flips the script entirely, suggesting dark matter isn't just hiding in space, it's slipping through cracks in time itself, existing a fraction of a second out of sync with the rest of reality. And if that's true, the first instance of time travel might not have been a cosmic cataclysm at all. It could have been as quiet as dark matter stepping through a temporal backdoor. Picture time not as a smooth river, but as a stack of film frames, each representing a fleeting moment. Normally, everything in the universe stays neatly aligned on the same frame, but dark matter might be different. Some models suggest these mysterious particles don't just move through space differently, they vibrate at frequencies slightly offset from our timeline, like a radio station broadcasting on a neighboring channel. Every interaction they almost have with normal matter isn't a miss, it's a near hit across time. A handshake that never quite connects because the hands exist in adjacent moments. This idea comes from the bizarre world of quantum field theory. Just as electrons exist in fuzzy probability clouds, dark matter might occupy a temporal haze, smeared across instants too brief for us to measure. In the chaos of the early universe, where space-time was still setting its rhythm, these particles could have gotten stuck between beats, forever out of phase. It's like trying to high-five someone who's always a fraction of a second ahead. You'll never touch, no matter how hard you try, and here's where it gets wild. If dark matter slipped between temporal layers in those first moments, it wouldn't just explain why it's so hard to detect. It might also solve one of cosmology's biggest mysteries: why galaxies hold together at all. Normally, stars on the edges of spinning galaxies should fling into space, but dark matter's gravitational pull keeps them anchored. If that pull comes from particles ever so slightly unmoored in time, their influence could stretch farther than physics allows in a single moment, like a cosmic anchor dragging across multiple frames of reality. The evidence: look to the cosmic microwave background. Its subtle irregularities might not just reflect density variations. They could be shadows of dark matter's temporal drift, imprinted when the universe was still soft enough for time to warp. Even more compelling, certain quantum experiments have caught particles behaving as if they're influenced by forces outside standard time, hinting at hidden layers where dark matter might operate. But the boldest implication isn't about the past, it's about the future. If dark matter dances between temporal layers, we might one day learn to sync with its rhythm. Imagine harnessing particles that naturally exist a heartbeat ahead or behind, building detectors that don't just search for dark matter in space, but in the gaps between moments. It wouldn't just rewrite physics, it'd prove time travel wasn't just the universe's first trick. It's been running in the background all along. The ekpyrotic universe theory sounds like something ripped from the pages of a sci-fi epic, but it's a serious cosmological model with a startling twist. Instead of a single, solitary Big Bang, this scenario proposes our universe was born from a cataclysmic collision between two higher-dimensional membranes, or branes, floating in a vast, unseen bulk dimension. Picture two sheets of paper suspended in a dark room, drifting closer until smack they slam together in an eruption of energy so violent it birthed everything we know. But here's the mind bender. If these brains carried their own separate timelines, that collision wasn't just a merger of space and matter. It was a fusion of histories, a cosmic time crash where two entirely different pasts collided to create our present. The math behind this comes from string theory's most radical extensions. In these models, our three-dimensional universe isn't floating alone. It's one of many brains existing in a higher dimensional space. Before the collision, each brain might have hosted its own version of time, with particles, forces, and even causality operating under different rules. When they smashed together, those timelines didn't just align, they entangled, stitching together moments that never should have met. Imagine two rivers of time, one flowing east, the other west, suddenly merging into a single, turbulent stream. The result, a universe where the beginning isn't a clean slate but a tangled knot of borrowed moments. Evidence for this might lurk in the cosmic microwave background. The ekpyrotic model predicts subtle differences in the radiation patterns compared to standard Big Bang inflation anisotropies that look less like random fluctuations and more like the scars of a brain collision. Some researchers even speculate that dark matter could be remnants of the other brain's physics, particles that slipped through the crash with properties just alien enough to evade detection. But the wildest implication isn't about the past, it's about the future. If our universe emerged from colliding brains, it might happen again. Somewhere in the higher dimensional bulk, another brain could be drifting toward us right now, carrying its own arrow of time, its own version of history. When it hits, the collision won't just reshape space. It could rewind, fracture, or even reset time itself, leaving future cosmologists to piece together which parts of reality were ours and which were borrowed from another timeline entirely. The Novikov self-consistency principle doesn't just constrain time travel, it turns the entire concept into a cosmic game of chess where the universe always wins. Picture this: you build a time machine, travel back to prevent a disaster, only to realize your very presence in the past was the disaster, setting in motion the exact events you tried to stop. That's the essence of Novikov's idea, not that the past resists change, but that it's already incorporated any attempts to alter it. Now, rewind to the Big Bang. What if the universe's first moments weren't just chaotic, but already self-correcting, weaving every potential paradox into the fabric of reality before time itself had fully formed? This principle springs from the heart of general relativity, where the laws of physics refuse to tolerate contradictions. If a time traveler's actions would create a paradox like killing their grandfather, the universe subtly adjusts probabilities to prevent it. A gun jams, a foot slips, a warning arrives just in time. It's not fate intervening, it's physics enforcing consistency, like a river rerouting around a boulder without breaking its flow. In the newborn cosmos, this might have been the norm. Quantum fluctuations, those random flickers of energy, could have flickered just so, guided by an invisible hand, ensuring they didn't contradict the universe's own existence. The cosmic microwave background's eerie uniformity, not just inflation's doing, but the signature of a reality that edited itself into coherence. Here's where it gets eerie. If the early universe was a swirling storm of potential paradoxes, Novikov's principle suggests they weren't avoided, they were pre-resolved. Every particle's path, every fluctuation's outcome, might have been locked into a self-consistent loop before causality even solidified. Think of it like a painter who accidentally spills ink, then incorporates the blotch into the masterpiece. The universe didn't erase its mistakes, it made them part of the design. This could explain why quantum particles seem to know their future states. They're not psychic, just bound by a timeline that's already reconciled all possible twists. The most unsettling implication: if self-consistency shaped the cosmos from the first instant, then free will might be an illusion woven into reality's framework. Every choice you make, every action you take, could feel spontaneous while being subtly nudged by the universe to maintain harmony. Even the Big Bang's fine-tuning the perfect balance of forces allowing life to exist might not be luck. It could be the only version of events where the universe didn't collapse under the weight of its own contradictions. And if that's true, then time travel isn't forbidden. It's just already happened. Every jump, every loop, every ripple might be invisibly threaded through history, their effects baked into reality since the very first second. So the next time you feel déjà vu, ask yourself, is it a glitch in your memory or the universe quietly ensuring you're right where you've always been? What if radiation, light, radio waves, even the heat from your morning coffee didn't just travel forward through time? That's the radical heart of the Wheeler-Feynman absorber theory, a concept so counterintuitive it suggests every burst of energy in the universe is secretly a two-way street, with half of its existence moving backward through time. Picture tossing a stone into a pond. Normally, you'd see ripples spreading outward, but this theory claims there's an invisible set of waves collapsing inward too, traveling in reverse to meet the moment of impact. Now imagine that happening with every photon emitted since the Big Bang, and you start to grasp the sheer scale of this idea. The theory hinges on a wild symmetry hidden in the equations of electromagnetism. When an electron jiggles, it emits radiation. That much we know. But Wheeler and Feynman proposed something bolder. That emission only happens because the entire universe is poised to absorb it. In their model, every forward-moving wave we see is matched by an advanced wave racing backward through time, a kind of cosmic echo confirming the energy will be absorbed in the future. It's as if the universe is a vast, self-regulating circuit where cause and effect aren't linear but looped, with the future whispering back to shape the past. Now rewind to the universe's first moments. In that seething plasma of particles and energy, this time's symmetric dance wouldn't just be happening, it might have been the glue holding reality together. Particles emitting light wouldn't just be broadcasting into the void, they'd be entangled in a feedback loop with their future absorbers, like a cosmic game of catch where the ball is thrown and caught simultaneously. This could explain why the early universe was so unfathomably dense and hot. It wasn't just expanding, it was a hall of mirrors where radiation reverberated between future and past, amplifying its own energy in a self-sustaining loop. The implications are staggering. If Wheeler and Feynman were right, the Big Bang's afterglow, the cosmic microwave background, might not just be a snapshot of the universe's youth. It could be a palimpsest of overlapping advanced and retarded waves, a fossilized echo of time's two-way flow. Even dark energy's mysterious push could be tied to this. As the universe expands, the balance between future absorbers and past emitters might subtly shift, altering the fabric of spacetime itself. Here's the twist that bends the mind. If the early universe relied on this time's symmetric feedback, then the arrow of time we experience today, the relentless march from past to future, might not be fundamental. It could be an emergent property, like the illusion of wetness emerging from countless water molecules. At the deepest level, reality might still be a conversation between moments, with the cosmos constantly negotiating its own history to maintain consistency. And that raises a haunting question. If the universe once spoke fluently in both directions of time, what silenced half the conversation? Could dark energy's grip or the sheer dilution of matter across space have muted the advanced waves, leaving only the forward flow we take for granted? Or are those whispers from the future still there, hidden in quantum noise, waiting for us to learn how to listen? Time crystals sound like something from a physicist's wildest dream, structures that repeat not just in space, but in time, ticking like eternal clocks without any energy input. But what if the very first structure in the universe wasn't a star, a galaxy, or even a particle? What if it was a time crystal so vast its oscillations didn't just mark time, they defined it? Picture the instant of the Big Bang, when reality was still a seething quantum foam, unshaped by the rules we know today. In that chaos, fluctuations weren't just random. They might have spontaneously organized into a pattern that repeated, not in space but across moments. This wouldn't be a crystal of atoms, but a crystal of time itself, its rhythm locking into place before clocks, before causality, even before the arrow of time had a direction. It's like the universe's first heartbeat, a pulse that set the tempo for everything to come. The math behind this is as elegant as it is strange. Time crystals, first proposed by Nobel laureate Frank Wilczek, break symmetry in a unique way. They're structures that oscillate at a set frequency without losing energy, forever out of step with the flow of time around them. In the extreme conditions of the early cosmos, where energy densities defied imagination, space-time itself could have crystallized into such a pattern. Think of it like freezing a wave in the ocean, except here, the wave is time's forward march, momentarily locked into a cycle of repetition. Here's where it gets mind-bending. If the universe's first structure was a time crystal, its oscillations wouldn't just be a curiosity, they'd be the scaffolding for causality. Every tick of this cosmic clock might have nudged particles into alignment, stitching together the first threads of cause and effect. Entanglement, the spooky connection between particles across space, could be a relic of this era, a leftover echo from when all particles danced to the same temporal rhythm. Even the uniformity of the cosmic microwave background, that afterglow of the Big Bang, might reflect the crystal's perfect repetitions, imprinted like grooves on a record. But the real kicker, time crystals aren't just ancient history. Labs have created microscopic versions in quantum systems, where atoms pulse in predictable cycles without energy input. If we can make them today, imagine how stable they'd be in the universe's first moments, where energy densities were 1 trillion times higher. Some theorists even suggest dark matter could be a shadow of this primordial time crystal particles forever out of sync with our timeline, their oscillations so vast we perceive them only as missing mass. And here's the twist: if time's flow was set by a crystal, it might not be immutable. Under the right conditions, like inside neutron stars or black hole horizons, space-time could still crystallize anew, creating pockets where time loops or stutters. The universe's first time travel wasn't a fluke. It might have been the first tick of a clock that never needed winding. The Higgs field isn't just what gives particles mass, it might be the reason time flows forward at all. Picture this: in the universe's first trillionth of a second, when everything was a seething, symmetrical soup of energy, the Higgs field did something extraordinary. It froze like a lake locking into ice, breaking the perfect symmetry of the early cosmos and giving particles their weight. But here's the twist: this phase shift didn't just shape matter. It could have been the moment time itself snapped into a one-way street, the first irreversible event that made past and future fundamentally different. Before this shift, the universe was a place of perfect symmetry where particles moved at light speed and the laws of physics worked the same forward and backward. Time had no arrow, no preferred direction, but as the cosmos cooled, the Higgs field settled into its frozen state like a ball rolling into the lowest point of a valley. That transition wasn't just a change in energy, it was a cosmic fork in the road, locking in conditions that made the future look different from the past. Suddenly, particles had mass, interactions slowed down, and entropy found its groove. The universe went from a featureless blur to a story with a beginning, middle, and end. The math behind this is staggering. Symmetry-breaking events like the Higgs transition create what physicists call goldstone bosons, particles that emerge from the cracks in broken symmetries. Usually, these are thought to govern forces like electromagnetism, but some theories suggest one of these leftover vibrations from the Higgs shift could have been time's first tick, a quantum whisper that set the entire cosmos ticking forward. It's as if the Higgs didn't just give mass to particles, it gave direction to time itself. Evidence for this might be hiding in the cosmic microwave background. The Higgs field's phase change released a burst of energy that should have left ripples in space-time gravitational waves we could detect with future observatories. If those waves carry patterns hinting at a preferred temporal direction, it would mean the Higgs didn't just shape the universe, it aimed time's arrow. But the wildest implication: if the Higgs field shift locked in time's flow, then reversing it, somehow melting that frozen state, might not just change particle physics. It could unravel causality itself, turning the universe back into a timeless sea where past and future blur into oblivion. And that raises a chilling question: if time's direction was set by a single event, what's stopping another? Roger Penrose's vision of the cosmos isn't just infinite, it's endlessly recyclable. His conformal cyclic cosmology, or CCC, paints a picture where universes don't just live and die, they reincarnate, with each death seeding the next Big Bang. But here's the twist: this isn't a simple reset. It's a cosmic inheritance where the final moments of one universe whisper directly into the first moments of the next. And that handoff, that's the universe's first time travel, a bridge between eons where the past reaches forward to shape the future. To grasp how radical this is, picture the universe's far, far future trillions of years from now. All stars have burned out, black holes have evaporated, only stray photons and ghostly neutrinos drift through an expanding void, their energy stretched so thin by the universe's expansion that space becomes featureless. In most models, this is the heat death, the end. But Penrose saw something else, a moment when the universe's vast scales become meaningless. With no matter or structure left, distance and time lose all practical meaning, so mathematically, this empty future state becomes indistinguishable from the singularity of a new Big Bang. It's as if the universe forgets how big it is, collapsing into a rebirth not by crunching down, but by becoming mathematically identical to a singularity. The magic happens in the conformal rescaling, a geometric trick where you stretch or shrink the universe's dimensions without changing its fundamental shape. At the end of time, this rescaling lets the infinite and the infinitesimal meet. The last fading photons of one era, stretched across light years, can be reinterpreted as the first frenzied particles of the next. The previous universe's death throws its gravitational waves. Its Hawking radiation become the seeds of new structure. It's like taking the final whisper of a dying man and amplifying it into the first cry of a newborn, all because the rules of scale momentarily dissolve. Evidence for this might be hiding in the cosmic microwave background. Penrose and collaborators claim to have found concentric circles in the CMB patterns of temperature variation that shouldn't exist if the Big Bang was a true beginning. These circles, they argue, are imprints of supermassive black hole collisions from the previous universe, their gravitational waves etched onto the newborn cosmos like scars passed between lifetimes. Critics argue these patterns could be statistical flukes, but if they're real, they'd be fossilized proof of cosmic reincarnation, the most mind-bending implication. If CCC is correct, then time isn't just cyclical, it's fractal. Each universe's timeline connects seamlessly to the next, with information, though scrambled, surviving the transition. The first time travel wasn't a journey within our universe, it was the moment the prior eon's death reached across the void of non-existence to birth our own. And if that's true, our universe is fine-tuning the precise constants allowing for stars, planets, and life might not be luck. It could be the result of an endless cycle of universes honing their physics across eternity, each iteration inheriting whispers of the last successes. But here's the haunting question. If time is an infinite loop of cosmic rebirth, are we living in the first iteration or the trillionth? And somewhere in the echoes of our own Big Bang are the faint, scrambled records of universes that came before, each one a chapter in a story without beginning or end. We normally think of observation as a passive act peering at reality without changing it. But in the quantum realm, the mere act of looking can freeze time itself. This is the quantum Zeno effect, named after the ancient Greek philosopher who argued motion was illusory because an arrow can't move if time is divided into infinitely small instants. In modern physics, it describes something just as paradoxical. A system under constant observation literally stops evolving, like a butterfly pinned mid-flight under a microscope's gaze. Now stretch that concept back to the universe's first moments, when reality was so fragile that even a quantum fluctuations glance could have pressed pause on time itself. Imagine the instant of creation, a frothing sea of potential where particles flicker in and out of existence too fast to measure. Normally, these fluctuations would vanish as quickly as they appear. But according to the quantum Zeno effect, if something observes them, even another fluctuation, their decay grinds to a halt. It's as if the universe, in trying to perceive itself, accidentally froze its own clock. The math behind this is both elegant and unsettling. Every quantum system has a probability of changing states, but continuous observation resets that probability, like a gambler eternally rolling dice but never letting them land. Apply this to the Big Bang's chaos and you get a staggering possibility. The first stable particles might not have emerged from cooling energy, but from reality watching itself too closely to keep changing. Here's where it gets stranger. In quantum physics, observation doesn't require a conscious mind, just an interaction that collapses probabilities into definite states. So what acted as the universe's first observer? One radical answer: nothing. The sheer density of the early cosmos meant every fluctuation was constantly observed by its neighbors, locking the quantum foam into a near stasis until inflation tore it apart. The cosmic microwave background's eerie uniformity, the fact that distant regions share the same temperature, might not be a coincidence. It could be the scar of a universe that paused just long enough to smooth its wrinkles before time unstuck and expansion began. But the most profound implication isn't about the past, it's about the nature of reality. If observation can halt time's flow, then existence might hinge on a delicate balance between watching and unseeing. Too much attention and the universe freezes, too little and it dissolves into noise. Perhaps we don't live in a cosmos that simply unfolds. We live in one that chooses to unfold moment by knowing just when to look away. From cosmic bounces to quantum whispers, from collapsing brains to time crystals pulsing beneath reality, we've journeyed through 30 mind-bending theories about the universe's first dance with time travel. Each one isn't just a wild guess, it's a window into how deeply strange and flexible time might truly be. Some see time as a river with whirlpools, others as a hall of mirrors, or even a code waiting to be rewritten. What's astonishing isn't just the variety, it's how many of these ideas are rooted in real math, real physics, and real observations of the cosmos. Whether it's dark matter slipping between moments, white holes vomiting space-time, or the universe literally bootstrapping itself into existence, one thing's clear: time might not be the steady, one-way street we assume. And that leads to the ultimate question: if the universe could bend, twist, or shatter time once, what's stopping it now? Could black holes still be stitching closed time-like curves into the fabric of space? Are there pockets of reality where entropy runs backward, hidden in the voids between galaxies? Or maybe the echoes of those first time loops linger in quantum entanglement, whispering secrets about causality we're only beginning to decode. So here's where you come in. Which theory bends your mind the most? Do you think the universe is a recycled echo of a past cosmos, or a hologram projecting time as an illusion? Drop your favorites in the comments, and if you're hungry for more cosmic mysteries, hit subscribe. Because the wildest part of all this, however time actually works, the truth is probably stranger than any of us can